Hi, I'll be presenting Lab 5 and my topic is the Slink Drop. So I'll discuss the physics principles behind this lab, and I'll go into the tracker model and the computer model, and then I'll make a comparison between the two, and lastly I'll answer the what does it mean question. So for the physics principles, I utilized Newton's second law, in which I incorporated the velocity update and the position update formulas in my code. So it's Vf equals F net over m times delta t, and Rf equals Ri plus V average times delta t. And I also considered the drag force. So the drag force will be in opposite direction to the slinky falling, basically opposing the motion. And so before the bottom of the slinky moves, F net is the weight force and the tension on the bottom of the slinky. And after the bottom of the slinky falls, the F net is the weight force and the drag force this time. And by weight force, I mean basically the force of gravity. And so here's the tracker. So I modeled the motion of the slinky falling from the YouTube video, and I specifically only tracked the bottom part of the slinky. So as in the bottom part is where the 0 position is, and I'm looking to see if the bottom part is also falling down as the top part is falling down, and at which point does the bottom part actually falls down. So it's at 4.7 seconds roughly when the bottom part of the slinky starts to fall, and that's when the Y position actually begins to decrease as it approaches the ground. And so for my initializations in my computer model, I had it set as the slinky's mass is 0.25, and I got the initial position from the tracker. The initial velocity is 0, and the delta t comes from the time frame in the tracker, and gravity is just 9.8, and the J hat is 010 because basically that's where like the bottom of the slinky is. It's like pointing upwards, and the proportionality constant I got basically from guess and check, and I got it to be approximately 25. And so 4.7 seconds is when the slinky begins to fall, like the bottom part. So before that, the net force is the weight and the tension force, which it's calculated by these two formulas listed, and I used the velocity update, the position update formulas, as well as updating the t, utilizing the delta t. And after the bottom part of the slinky begins to move, the time is basically between 4.7 and 6.5, and that's where like the video kind of ends. And so this time the net force is the weight plus the drag force, and the formulas are also listed here, and I utilized again the velocity update and the position update formulas, and I also advanced the time. And so you can see here that the net force formulas kind of differ from each other based on if the slinky was motionless or not. And so comparison between the tracker and the computer model graphs. So the computer model is the light green one, and the tracker is the darker green one. And basically the tracker, it's supposed to have also like a horizontal line up till 4.7 seconds roughly, but because my hand's a little bit shaky, I couldn't really like keep it on the same spot, but it was basically just motionless up till 4.7, and after it the slinky begins to fall down, like the bottom part, and this is reflected in both the tracker and the computer model, as you can see. And so for the finally what does it mean question, so the bottom part of the slinky is motionless as net force is 0 until the top part of the slinky begins to pile down through compression, and at which point it starts to affect the bottom part. And so that's when the slinky begins to feel the weight of gravity and also experience the drag force as the bottom part begins to fall down. And both the computer and the tracker model share the same trend line, meaning that what I consider to be the net forces like both before and after the bottom part of the Slinky moving is correct because it's reflected in the real life or the real world Slinky's motion. And thank you.